dedicated.
And
Okay.
my poor dog is not doing well, so.
Oh no, isn't that dog like a puppy?
She's a year and, is it 5 months, I think? Yeah.
What happened?
She needs to be on some probiotics, and she needed to get some nausea medication because she was like throwing up all day today.
Oh my.
So,
But she's gonna be okay though.
yeah. Oh yeah.
Oh, okay. So it's not like she's knocking on death's door. Yikes.
Yeah, she'll be fine.
Okay. Well, that's good. I thought you were going to say that the prognosis was not good. All right. So you are trying to show, okay, so you know that this diverges. Choose a series to which the comparison test can be applied when you're comparing it to this one. So this is the one that you know diverges. So you're trying to find a series in this list that is greater than the one that you know diverges. So your goal is to find a series in this list which is greater than 1 over k. So if you're comparing them, let's see, I don't even see. If you're looking at, let's see, we're talking about the two that diverge. So we already said that we knew it was going to diverge. And the question was regarding this one or this one. Okay, so when you're comparing the two, this one has the larger denominator. I am sharing my screen, right? Sorry, too many windows open. Okay, this one has the larger denominator, so this one's going to have the smaller ratio. So you're going to have this situation with the plus. This one's got the smaller denominator, so it's going to have the larger ratio, which means you're going to have this situation, at least maybe with, it might not be strict, but so the series that you should choose is the one that's greater than your comparison series, which would be the minus variation.
Oh, okay. I see where I went wrong now. For some reason, I had thought that we were trying to find a series to compare to the harmonic series, which is weird because we already know that the harmonic series diverges. So I like flipped it in my head. So I didn't like notice, or like it didn't like click inside my head that the harmonic series you gave us was the one we were comparing it to, and we were trying to find the series like to actually do the comparison test with.
I
So
see.
I see
So
where I went wrong.
because the question was sort of asked in reverse, you mean?
Yeah, that's what I meant.
Okay. All right. Okay. Yeah, because I mean, really about this particular series, I mean, this is one where I would be giving you the series on the left and then asking you to compare it to something that would be more like what's on the right. So you'd be choosing the harmonic series. So that's not one that I would ask you to compare to something more complicated. Your comparison series is always going to be something that's more basic. Were there any other questions about that? I want to make sure that's clear with the comparison test.
Just quick question. The homework for 8384, like the last couple of questions, is that what it's looking for too, for us to pick?
Yes, if I remember correctly, I did get at least, I think it was just one email question about those. So it's kind of, yes, because those come at the end of that assignment. Yes, Becky. Same idea.
Cool. That makes more sense then.
Yeah, and if I'm looking at those, I'm pulling them up right now. Those are slightly different because you have more than one option available to you, but because sometimes I'm having issues with these D2L quizzes, I didn't want to write one that had a multiple select to it and then have it not work right. So I just ended up only giving you the one that would work. Okay, but so it sounds like the rest of the quiz was okay. Were there any other questions on the quiz?
If you want to go over the last one, that'd be cool too. I mean, I know what the answer should have been because I marked it wrong, but visually seeing it again, that would make more sense.
Let me see. Find the sum of the convergence series. This one is telescoping. So you're going from k equals 1 to infinity of 1 over 4 to the k plus 1 minus 1 over 4 to the k. Okay. So for the telescoping series, and I mentioned it before, but it bears repeating. If you see a series automatically that's written as a subtraction of two terms, you should be thinking telescoping series. And you're going to get so used to applying these other tests that sometimes telescoping series gets lost in the mix and you forget about it. But anytime you're automatically presented with two terms, it's probably a telescoping series, especially if you have a subtraction between them. Now, you could also work this out to discuss the convergence or divergence just by thinking about it in terms of a geometric series, but I believe this one was presented in your text with telescoping, so we'll just do that. Okay, so start out by writing out your terms with k equals 1. So your first term will be 1 over 4 to the second power, which is 1/16, and then the second term with k equals 1 will be 1/4. And so this is when k equals 1. Add that to the k equals 2 term. So then you'll get 1 over 4 cubed, which is 1 over 64. If you find it more useful, you can just write it as 4 cubed instead of actually evaluating all these. And then minus 1 over 4 squared, which in this case would be 16. So you're actually going to see something slightly different than what I showed you in the class example, just because you're going to end up having these cancel slightly differently because you have the k plus 1 in the denominator of the first term instead of the second. And then if you were to do the k equals 3 term, just to sort of verify what was going on with your terms, you'd have k to the 4 to the 4th in this case, which is 256. And then 4 cubed. And then you could just keep going and going and going, and eventually you'd end up at the k plus 1 and the kth, or I'm sorry, the kth term. I didn't mean to say the kth plus 1 term. If you'd like, you can just say k equals n and then just sort of chop it off there. And then just sort of indicate that that behavior continues as you proceed down the line. And then you can start to cancel things out. So the 16 and the negative 6, I'm sorry, the 1/16 and the negative 1/16 are going to cancel. And then you'll get the positive 1/64 and the negative 1/64 to cancel. If you were to write out the fourth term, you would notice that 4 to the 4th, again, you'd get 256 in the denominator, and eventually that 256 would be canceling out as well. Now, remember I told you that with telescoping series, these are going to cancel symmetrically on the right and the left. Now, if you accidentally do this wrong, it's not going to be a big deal because whether you keep the 1 over 4 to the n plus 1 or the 1 over 4 to the n is not going to make a difference in this case because the limit's going to end up being the same, unfortunately. But if we cancel these out symmetrically, that last term with the negative 1 over 4 to the n is going to be one that cancels. And then you're still going to have this second to last term of 1 over 4 to the n plus 1. Now you can take the limit as n approaches infinity of the terms that remain. So you would have negative 1/4 and then plus 1/4 to the n plus 1. And then as you take the limit, and for the first term, you're just taking the limit of a constant, which is going to be the constant itself. And then for the next term, you're taking 4 to the infinity, and you're taking 1 and you're dividing by that quantity. You're just going to get 0. So you're going to find that the sum of your convergent series, if you use it as a telescoping series, will be negative 1/4. Which was the way that I intended for you to do it, but you could have also thought about this in terms of geometric series. Okay, but always good to go over the telescoping series. Anything else from the quiz? You're welcome.
Yeah, for the second one, I was just forgot the whole continuous positive and non-increasing part, because I was just thinking I can get the integral of that, but no, it's actually it's positive, it's not increasing, but it isn't continuous. This 1/k-2. So
right, yeah, I know. And these, I don't know. I was gonna say these just 2 answer problems, yes or no, sometimes are even worse than having 4 options. But because you just have 1 to choose from, or 2 to choose from, you pick 1. Yeah, so whether it's positive and non-decreasing or non-increasing in this case doesn't matter, because the function's not continuous on this domain from 1 to infinity. Yeah, exactly.
You know what's funny is I wrote down the 3 little boxes and the wording, and I went through them, checking them off.
Mm-hmm. That's good. You should be getting into that habit. Yeah, and of course I didn't make you do one with the integral test on the quiz because I can't enforce that. I can't see your work, so it doesn't really make sense except to just kind of ask you a general question about the integral test. Okay, so if there are no other questions, I'm going to talk about the limit comparison test in section 4. So on the asynchronous video, I covered the general comparison test, which we usually refer to as the direct comparison test. Your book just calls it the comparison test. Now that's different from the limit comparison test. So I'm going to give you a theorem for that, and then we'll apply it to some examples. And I told you I really like the limit comparison test, and I don't know why. I guess just because I find it so useful. Okay, so here's your theorem. Limit comparison test. And I know people don't like limits, so maybe you feel like you're going to hate this. You're not going to hate this. You're going to love it. You're going to learn to love it. Okay, suppose that the series from 1 to infinity of a sub k and the series from 1 to infinity of b sub k, let's remember we have to have comparisons here, are both series of positive terms. All right, so we have 3 conditions here. The one you're going to see most often is the first condition, which I'm going to show you the most examples of, but I'm also going to show you an example of the other 2, just to make sure that we understand how to use it. If the limit as n approaches infinity of a sub n over b sub n is equal to some number L. Now, it's important that we note L is some positive finite value, L is some number between 0 and infinity, then both series converge or both series diverge. So whatever one series does, the other one also does. And remember, you're choosing a comparison series because it's a series you know something about. So you're going to know if it converges or diverges. Your question is basically going to be, well, what's happening to A sub n? I know what's happening to B sub n. What's happening to A sub n? So you're going to take the limit of the ratio of the two. And if you get some finite value, then doesn't matter what the value is. What the value is doesn't tell you the sum of the series, by the way. It just tells you whether the series converges or diverges. So that's the way this will work. I'm going to give you two other conditions. Sometimes you'll go to use the limit comparison test and you'll get very frustrated because you're going to get a limit of 0 and you'll be like, ugh, I guess I can't use the test. Well, not necessarily. If you take the limit as n approaches infinity of A sub n over B sub n, and you do end up getting 0, and if your comparison series, the one you chose, B sub k, converges, then you're going to get convergence for A sub k. So even though getting a limit of 0 is not great, it could be just fine, assuming that your comparison series converges. So if your comparison converges and you get a limit of 0, well then both series are going to converge. So that's one option. Now, if you get a limit of 0 and your comparison series diverges, well, then we can't say anything. Either you need to use another test or you need to find a new comparison series, one that maybe does something differently than what you would expect, or maybe has a different limit. Because sometimes you know whether you're expecting your series to converge or diverge, but sometimes you don't know. Sometimes you're kind of like, might converge, might diverge, I'm not sure. So, I mean, maybe it could be the fact that you just chose a comparison series that converged, and you could try one that diverges. And I'm going to show you an example where you kind of don't know, and you're going to have to just work your way through it using one of these conditions. The other possibility would be if the limit as n approaches infinity of A sub n over B sub n is infinity. So that also is a bummer because that'll happen sometimes, and I don't want you to think like, oh, I can't use the limit comparison test now. Well, that's not necessarily true, but it must be the case that if you use the limit comparison test and your limit is infinity, then your comparison series has to diverge in order to give you any sort of conclusion about your series. So we would say, and if your comparison series from 1 to infinity of B sub k diverges, well, then you can make a conclusion about your series, A sub k, diverging. But if you get infinity and your comparison series converges, well, you're out of luck. You're going to have to think of something else. Okay, I was trying to think if I showed you guys a particular series last time. Oh yes, okay. All right, so let's dig into this limit comparison test. We'll show you some examples of how it works, kind of contrast it with direct comparison. The reason I really like limit comparison is because sometimes direct comparison, it seems like it should be such an obvious thing to show, but sometimes it's hard to show that your series is greater than one that diverges or less than one that converges. Limit comparison, you don't have that issue. So, gosh, I don't remember where I left off. Let me check. I think it's example number 5. But maybe not. Let me see. 2, 3. Oh no, I did 3 examples. So since we're still in 8.4, call this example 4. Okay. I must have been running out of time because I had a different example here that I was going to do, and apparently I did not do it. But that's okay. I'm going to give you the series from, it's going to look really similar to what we did in example 1. We're going to go from 1 to infinity, but this time I'm going to switch it to 2n squared minus 1 in the denominator. Okay, now when we did something really similar to this in example 1, in the denominator we had 2n squared plus 1. And when we pulled that out for a comparison, I'm going to say recall, in example 1, we had this series of 2k squared, k squared plus 1. And when we had that, we pulled the series out and we said, okay, well, let's see, we have 2k squared plus 1. And then we felt like, okay, this probably converges because it looks just like a p series would. The 1's not really affecting anything. So we just needed to show that this series was less than one that we knew converged. So we lopped off the 1 and then we took off the 2. And we said, okay, well, this must be the case. This denominator is larger because it's being multiplied by 2 versus that one. And this one's larger because it's got an extra 1 on it. And then we said that we knew that that converged. And then we used the comparison test on it. Voila, done. This changes a little bit, however. It makes it slightly more complicated just because you have a minus 1 on this. So now you're in the situation where you're looking at 2k squared minus 1, and you're trying to show that this is less than 1 over k squared. Now, writing out a couple of terms of this, or even just getting some sort of general formula for this in k, you would be able to quickly show that, but well, maybe not that quickly, but you would be able to show that this is true. But it's not the quick, obvious situation that we had in example 1, because now you're saying, okay, well, we're subtracting 1 in the denominator. If I'm subtracting 1, well, then I can't say that this is true because this denominator is less, so the ratio would be more. And it would be harder to make that leap to get from here to here. And then to make the leap that goes from here to there is even less straightforward, just because you would have to make some general statements about the way those numbers all sort of cooperate with each other. The fastest thing to do here would be to use the limit comparison test with this series. So we're going to say use as a comparison series. And we know that this converges, but instead of using direct comparison, we'll use limit comparison. Okay, so what we're going to do is we're going to take the limit And if you want to use n or you want to use k, it does not matter. I already have it written out as k. So we'll send k off to infinity. And what we're going to do is we're going to take our series, which is 1 over 2k squared minus 1, and we're going to divide it by the comparison series, which is 1 over k squared. You're going to do this so often that you're probably going to skip the step where you write it as a ratio of two fractions, and you're probably just going to invert and multiply without doing this step. And I'm okay with that because I understand that you're going to be doing a ton of this. You're going to be doing even more of it when we get into 8.6 when you're using the ratio test. You're going to be taking a lot of ratios of series. So when you invert and multiply, you're multiplying, and you're, instead of dividing by 1 over k squared, you're multiplying by k squared over 1. So you're going to have k squared in the numerator, and in the denominator, you have 2k squared minus 1. Now when you take the limit, you can use the ratio of the lead coefficients and get 1/2. And this is between 0 and infinity. Therefore, you would say that both series converge by limit comparison. So hence, both series converge by limit comparison. So notice that the limit comparison test is a completely different test than using the direct comparison test that you were shown in the previous lecture. Are there any questions on example 4? So I wanted to start out with something that was really basic. I'm going to build on that, but nothing too crazy yet. For example 5. These generally don't get super crazy anyway. Example 5. Mostly I just want you to get used to these ratios and taking these limits. So your series, and we'll just use n this time, because I know I'm just going to end up writing n's anyway, is going to go from 1 to infinity. In the numerator, you have 5n to the 4th minus 2n squared plus 3. And in the denominator, you have 2n to the 6th minus n plus 5. I also really want to get you comfortable with just finding a comparison series altogether. And hopefully, if you did the homework from 8.3, or I'm sorry, it was 8.3, 8.4. It was, I think, only 4 or 5 questions on 8.4, just to sort of get your feet wet with that comparison test. But it's really important that we're able to generate that comparison series that's going to work for us. So what you're going to do is, and I'm going to rewrite my whole series, 5n to the 4th minus 2n squared plus 3 divided by 2n to the 6th minus n plus 5. And what I'm going to do is I'm just going to start lopping off terms that are going to be affecting the way this series grows or gets smaller less rapidly. So for instance, the constants aren't really doing much for me as far as really affecting the direction of this function. So I'm going to get rid of them. Anything that's not a lead term, I don't want to worry about right now, because what's happening with n squared is going to affect the numerator much less than what's happening with n to the 4th. So I know you're thinking like, well, it is a minus, so it's pulling that numerator down. Yeah, but it's pulling it down much more slowly than 5n to the 4th is bringing it up. So this numerator is really being controlled by 5n to the 4th, not what's coming off of it with minus 2n squared. Same thing in the denominator. The growth is really being affected by 2n to the 6th. The n, not really affecting things. So you're going to say that, all right, this is not the same as, but we'll say that it's kind of like 5n to the 4th over 2n to the 6th. And then you're going to start canceling some ends. So once you have this broken down into just one term over another term, you can start canceling stuff out and say, okay, well, now this just looks like 5 over 2n squared. And if you want, even since you know the constants aren't really doing anything for you, you can say that this is really just kind of like 1 over n squared. If you want to go that far with it, which I think you should. So this is going to be your comparison series. And it converges because it's a p series where p is greater than 1. P equals 2, for those of you who don't remember. So this is what we're going to compare our series with. So you're going to take the limit as n approaches infinity of the ratio of these two. Before I do that, does anybody have a question so far?
Nope.
All right. So let's go ahead and take this ratio. Now, when you're doing this, you have to start out with your entire series. You can't just start cutting corners. I need to write this whole series that I originally started out with as a sub n. And because this is still very new, I'm going to write out the whole ratio, and then I'm going to invert and multiply. So we're taking our series, and we're going to divide it by the comparison series, which is 1 over n squared. And again, like I said, you don't have to show this full step. If you'd like, you can automatically go to multiplying by the reciprocal. I always write more steps just because I'm the teacher. So we'll just multiply by n squared over 1, which is the same as n squared. And then you're going to simplify that. So you're going to multiply n squared into these 3 terms to the left of n squared. So you're going to end up getting 5n to the 6th minus 2n to the 4th plus 3n squared divided by 2n to the 6th minus n plus 5. And then again, if you find it useful, which I always do, you can use that rule from algebra that says that if the degree is the same in the numerator and the denominator, then the limit as n approaches infinity is the ratio of the lead coefficients. So in this case, my limit, we could say, is 5/2. And now remember, this is not the sum of the series. This is arbitrary because it's all based on my comparison. I could have compared it to 5 over 2n squared, and I would have gotten a different limit. So this has nothing to do with the sum of the series. All this is doing is showing that both of our series converge. All we're looking for is what's the value of the limit. If it's positive and finite, then it must be the case that both of our series do the same thing. If it's 0 or infinity, then we have other things that we need to verify before we can make a conclusion. So this is positive and finite, so we would say that both series converge. I want to do one with some radicals because I want you guys to also get used to working with radicals as you run through your limits. Before I do another one, does anyone have a question on example 5?
Nope.
All right. So for example 6, we will look at the series from n equals 1 to infinity. In the numerator, we'll have 3n squared minus n And then the denominator will have the square root of n to the 5th plus 2n. So the first thing I want you to do is find your comparison series. So we're going to start with our series, and then we're going to start lopping off anything that's not a lead term in the numerator and the denominator. So lop off the n, lop off the 2n. Now, I'm not canceling in this case. I'm just getting rid of any additional terms that are having less effect on what's happening to the function. So that leaves me with 3n squared divided by the square root of n to the 5th. And keep in mind, by the way, that this has to be written in descending order in order for you to always be looking at the terms that are on the right. So if this was not written in descending order, you could rewrite it or just be careful with what you end up lopping off. Okay, remember that the square root of n to the 5th is going to be n to the 5/2. A square root is always going to be a 1/2 power. And then the exponent inside the radical is going to be the numerator of the rational exponent. And then you're going to simplify again. So I know that 3n squared, if I divide it by n to the 5/2, will simplify so that I have only 1/2 power on n in the denominator. Remember, 5/2 is 2.5. Get rid of 2 of those, and you'll just have 1/2 left over. Or you can use that rule from algebra that says that if you're dividing and you have the same base, you subtract the exponents. So 2 minus 5/2 is -1/2, and a negative exponent will go into the denominator. And if you'd like, you can even get rid of this 3. It does not matter. Whatever you want to do. Now, this is going to be your comparison series, and this one diverges. It's a p-series where p equals 1/2, which is less than or equal to 1, less than, but it's going to diverge as long as it's less than or equal to 1. So we're expecting that our series is also going to diverge, just because we've compared it to this one. It looks like we're seeing this behavior occurring in our series. We just need to prove that by using the limit comparison test. Before I apply the test, are there any questions on how I obtained the comparison series? Okay. Wonderful. All right, so we're going to take the limit here, and this is where this one's actually a little bit trickier with the limit, just because you're going to be working with these radicals. So you have 3n squared minus n divided by the square root of n to the 5th plus 2n, and we're going to divide that by, if you want to use the square root of n, you can. I think I will, just because I already have radicals going on here, but it doesn't matter. You can use n to the 1/2 if you'd like. So we'll have 3n squared minus n divided by the square root of n to the 5th plus 2n times the square root of n. The reason I really wanted to focus on this was because a lot of students tend to cut corners when they're working on limits with radicals. And I really want you to justify your work here and not just say like, well, this is technically happening and it's clear that this is happening. Because if you could just do that, then we would just look at this and say, okay, it clearly diverges. But we're not doing that. We have to actually support our work with mathematical conclusions. So we're going to go through and actually find this limit. If I were you, oh, by the way, you actually learned how to find these limits in Calc 1. You probably don't remember, but you did a lot of work with finding limits that involve radical functions. So if you remember that, I'm going to sort of bring you back there mentally. You have a couple options. First of all, I'm going to multiply this in just so that we have one fraction. I don't want this to be all discombobulated with two different factors. So we can go ahead and multiply it in, and you'll get 3 times n to the, well, this is n squared, and there's n to the 1/2. If you're multiplying and you have the same base, you add the exponents. So that's 3n to the 5/2 minus n to the 3/2. So you have 1 plus 1/2 is 3/2 divided by the 5th, or not the 5th root, the square root of n to the 5th plus 2n. Now, this is one of those where if you try to take the limit, you'll just get infinity minus infinity divided by the square root of infinity plus infinity. And if you try to use L'Hopital's rule, because it has a radical, you're going to end up with that situation where your radical is just moving around in the fraction endlessly. So you're going to have to simplify that out. And the way we usually do that is by dividing by the highest power that we see on our variable in the denominator. And if you want, you can even pull this out of the limit for a minute. I might do that just because I don't want to keep writing my limit. It's my trick. So if I wanted to do that, I could just say, all right, well, I have n to the 5th plus 2n, and I'll divide by n to the 5th in both terms in the denominator. But what I do in the denominator, I must also do in the numerator. Now, if you'll remember from Calc 1, when you divide by n to the 5th in the denominator under the radical, you didn't actually divide by n to the 5th. You divided by the square root of n to the 5th, which is n to the 5/2. So that's also what you're going to divide by in the numerator. Now, the whole point here is you're trying to get more powers in the denominator so that you can get some terms to zero out when you take the limit. That is the goal. If you're trying to remember what section this was from Calc 1, if you want to look back at your Calc 1 notes, if you're going through these limits and you find that you're stuck, I think it was 3/5, but let me verify. 2/5. Not 3/5, 2/5. Two-7. There's no 2/7. I used to know every single section, but they keep switching books on me now, and I'm now getting all the sections confused. I might just say, go find it yourself. Oh, it's limit laws. That's why it's chapter 1 in this book. It is section 1.5. So that's where we did all the limits at infinity in Calc 1. So feel free to go back to section 1.5 and just look through some examples if you find this to be weird. All right, so now when you divide this out, n to the 5/2 divided by itself just gives you 3, and then minus, well, 3/2 minus 5/2 is going to get you to -2/2, which is -1. So you'll have 3 minus 1 over n. And then in the denominator, you'll have the square root of 1 plus 2 over n to the 4th. And now if you want to put your limit back on, you can do that. So for the second term in the numerator, you're dividing by infinity, 1 divided by infinity as n approaches, well, as n approaches infinity, the limit of 1 over n is going to be 0. So in the numerator, you'll have 3, and in the denominator, you'll have the square root of 1 plus 0, which is just the square root of 1. So you end up with 3 here. Again, the value of the limit itself does not matter. It just matters that it's finite and positive. And as long as you've made that conclusion, we said that we had a comparison series that was a p-series with p equals 1/2. It diverged. So we could say that hence both series diverge by limit comparison. Questions on that one? The technique here was to divide by the highest power of n in the denominator. So whatever that was, you divide the whole fraction, every single term, by that quantity. Okay. Let's see what else I have for you. Yeah, I'm trying to show you some that have just some different sorts of algebraic techniques, so you get used to seeing them, or at least you have seen them, and hopefully if you see them again, you'll think back to your notes. So this will be example 7. This is the series. We'll go from 1 to infinity of 2 to the n plus 1 divided by 5 to the n plus 1. Oh, I wish I was seeing you guys in person. I would bring in so much Halloween candy. The house is just covered in Halloween candy. It's so bad. And I'm drinking a McDonald's beverage right now. I'm telling you, it all just, like, my whole body is just like, what's going on here? There's too much sugar. It's crazy. Oh, it's terrible.
I actually ran out of Halloween candy within the first hour and 15 minutes.
Someone else told me that too. They were like, we never get trick-or-treaters, and all of a sudden we got so many.
Yeah, I made 81 bags of treats. I had like 4 pieces of candy. I had like a little, some had like a rubber ball that had like an eyeball on it. I had like little different treats, and I ran out. It was fast.
I mean, my 6-year-old, he went trick-or-treating, but he really wanted to pass out candy. So he came back home, and just like people just kept walking by. They were on the north side of the street, but not on our side of the street. And he was totally bummed, and we have all the candy. And it was, even when I was trick-or-treating, every street we went on, everybody was on the north side and not the south side of the street. I couldn't figure it out. It's just excessive.
That's funny. Yeah, I had a table outside, and I put all the bags on the table, and I just sat out in a chair. I'm like, take one.
Well, as long as you were out there, because you know there are those rogue kids who
Oh yeah, that'll take like everything.
they take all the bags. Exactly. All right. Just felt like I needed to tell you about how this sugar thing, it's not good for me. It's terrible. It's because I'm getting older. I can't handle it like I used to. All right, take your series out. Both of these have a +1 on, where both the numerator and denominator have the +1. Obviously, that's not really affecting the behavior. And hopefully, when you see something like 2 to the n over 5 to the n, you're thinking like, oh, this looks geometric, and you'd be right. So rewrite this as a fraction to a power. So remember, you can always distribute that exponent to both parts of your fraction. You could also, I don't want to say factor it, but you could just sort of condense it so that you're taking that quantity to a power. All right, so now if we were to look at this series, we would know that this is a convergent geometric series. Remember that for the geometric series, we're looking for this value to be less than 1 in order for our series to converge, which it is. So now we're going to apply the limit comparison test with the series. Now, when I apply the limit comparison test, I'm going to go back to using this form just because this is the form that the original series is in, and it's not really going to be very helpful for us to use a ratio where we end up with this fraction that's being taken to a power. You can do it, but I feel like it's going to be easier to do it this way. And this limit can be a little tricky. So I wanted to show you this one specifically. All right, so there's our series, and we're going to divide it now by 2 to the n over 5 to the n. All right, so now when we rewrite this, we're going to show it being multiplied by 5 to the n over 2 to the n. And I want you to be very, very careful here, because what tends to happen with a problem like this is students say, oh, well, 2 to the n in the numerator, 2 to the n in the denominator, and they cancel them out. Remember, though, you can't cancel between terms. This is a collective unit. This is a collective unit. You can't just say, oh, I'm going to get rid of 2 to the n in both cases. And then they're like, oh, 2 to the n's cancel, 5 to the n's cancel, the limit's 1. Everything's great. You cannot do that. It's not mathematically legal. So you're going to have to combine these in a more meaningful way. So what we can do is, again, just use a little more algebra and distribute these quantities into the parentheses on the left. So I can say that this is 2 to the n times 5 to the n plus 5 to the n divided by 2 to the n times 5 to the n plus 2 to the n. And you have to get to a point where you know that you've justified this without just saying like, oh, well, clearly this is happening, because I don't want any sort of arguments like that. So we're going to undo this using a similar property to what we did over here. If you are multiplying, you have the same exponent, then you can combine those. So 2 to the n times 5 to the n, I can write as 10 to the n. And then you're still stuck. This is not really a situation where you can use L'Hopital's rule, and most of us don't remember these derivatives anyway for these exponential functions, but that's okay. What we're going to do is we're going to use the same type of reasoning that we used in the last example where we had radicals. This time we're just going to divide by the highest base that we see. Because what I want to do here is I want to get into another situation where I only have these variables in the denominator and I can get some of these limits to zero out. So I'm going to rewrite this. I know I just keep rewriting my limits. You don't have to do that. You can just pull your expression out. I'm going to divide each term by 10 to the nth power. And this is not the only way to do this. This is just the way that I think is the most straightforward. But we're dividing each term by the largest base value to that power. Now, the nice thing here is that when we do that, you can see that 10 to the n over 10 to the n is going to end up giving you 1. And then over here for 5 to the n over 10 to the n, we can do the same sort of thing that we did up top, where we can then just say that we have some quantity to the nth power by simplifying that out. Okay. So I have 1 plus, and then 5 to the n over 10 to the n is 1/2 to the n. And you talked about these limits. I want to say it was in 8.1 when we were talking about sequences. And then you have 1/5 to the nth power. Now, if you're thinking like, how does this help? We're still in a L'Hopital situation. We're actually not, because remember, and I'm pretty sure it was 8.1 where this was discussed. If you're applying, if you're looking at this limit as n approaches infinity, remember that when you're taking a value that's less than 1 to the infinity, each time you keep approaching infinity, this value is going to keep getting smaller. So like, let's say n equals 1, you have a half. Well, if n equals 2, then you have 1/4. If n equals 3, you have 1/8. So as n gets increasingly large, this ratio is going to get increasingly small because we're talking about a value that's less than 1. So we would say that that term right there, 1/2 to the n, would actually go to 0. And we could say the same thing in the denominator, that this term would actually go to 0 because 1/5 to the n, as n keeps getting larger, well, 1/5 to the n is going to eventually head off to 0. And we can conclude that our limit is 1. I know you wanted to do it a long time ago, but it was not mathematically valid to do so. But then we can say that hence both series converge. And I have another one I wanted to show you here that I thought might be a little bit tricky to find a comparison for, and it was another radical function. Let me go over that. Before I do that, are there questions on example 7? Notice I'm doing a lot more with limit comparison than just with the comparison test, just because I feel like it just can be applied to more functions. There's just more you can do with it. All right, example 8. I'm going to do this one, and then I'm going to show you those instances where your limit is 0 or infinity, so you can kind of see how that works. This one is going to be the series from 1 to infinity of 5 divided by n plus the square root of n squared plus 4. All right, so the most important thing here is to find an appropriate comparison series. So let's go ahead and lop off the constant here. I'm going to get rid of the plus 4. You can keep the 5 if you want. It doesn't matter. You can call it a 1. If you take off the 4, you're just left with n plus the square root of n squared in the denominator. But remember that the square root of n squared is just going to be n to the first power. And then be careful here because this is not n squared, it's just 2n. Because you're adding and not multiplying. So we'll say that this is approximately 1 over n because the constant multiples 5 and 2 aren't going to affect the convergence or divergence. Now we know this is the harmonic series, which is divergent. Now it's going to be the comparison. Any questions on finding the comparison series? Wonderful. So let's take the limit. If you want to wait to put the limit on, that's fine. Go ahead and write the ratio out. And then divide that by 1 over n. And you can rewrite it by multiplying by n. Which is 5n divided by n plus the square root of n squared plus 4. And if you want, just so we can see the limit, I'm going to pop it on there. In this case, you would have infinity divided by infinity plus infinity. You could try to use L'Hopital's rule, but again, you have a situation with the radical. So it's going to be most beneficial to you to divide by the highest power of n that you see in the denominator. So I'm going to do that now. Notice that in the denominator, under the radical, you have n squared. But since you're taking a square root, this would just be the square root of n squared, which ends up being n when you divide it everywhere else. So under the radical, I'm going to divide by n squared. So I'm going to keep it under the radical, but everywhere else, I'm going to divide by n. Remember, the square root of n squared is n. So I'm going to take 5 and divide it by n. And then in the denominator, I'll have n divided by n plus the square root of n squared plus 4. And in the radical, I'm going to divide each term by n squared because I'm underneath the radical in that case. And now I'm ready to take the limit. So I have 5 over n, and that's going to work nicely for me in the numerator because remember that when we have a constant divided by n and n's approaching infinity, that constant is going to approach. Wait, did I lose an n? Yikes! Sorry, I had an
Yeah,
n
you
here.
did.
Yeah, I was like, wait a second, approaches 0. I wasn't ready for that yet. Okay, just 5. Sorry about that. So I had a 5n, I divided by n. I had an n, I divided by n. And then in the two terms in the radical, I divided by n squared. Sorry about that. So we're taking the limit of 5 divided by 1 plus the square root of 1 plus 4 over n squared. And the nice thing is you will get a finite value. You'll have 1 plus the square root of 1. Remember that this term 4 over n squared, as n approaches infinity, goes to 0. You can write that if you'd like. But you end up getting the quantity 5 halves, which is indeed finite and positive. So we would say that both series diverge. Okay, and as promised, I want to show you 2 examples where you get limits to be either 0 or infinity. I want to show you one of each. Questions on example 8 before I move on? Okay, so even though really we're working on limit comparison tests here, a lot of what we're really focusing on is just figuring out what the comparison series should be. And then just honestly, in some cases, just figuring out how to find the limit. Because even though you can come up with a comparison, if you can't actually figure out what the limit is, then what can you do with it? You're stuck. And that's one of those algebra things where I always say calculus isn't hard because of the calc, the algebra. Example 9. This is the series from n equals 2 to infinity of 1 plus n times the natural log of n. We always need to do more of these natural log examples because I feel like they're a little more challenging. Divided by n squared plus 5. And I think if you see enough of these problems with the natural logs, you start to get the hang of knowing what to do when you see them. But I'm going to give you 2 right now so that you see 2 more and hopefully get a good sense of how to work with them as far as finding your comparison series. All right, I'm taking my series out. I'm going to find a comparison series. I'm going to take off the constants first. And I'm going to say this is approximately equal to n times the natural log of n divided by n squared. Now, once I take off the constants, now I can go ahead and get rid of the common factor of n in each one of these terms. So I can say I have ln n over n. Now, this is where it gets a little bit trickier because when there's a natural log involved, there are a lot of different ways in which you could compare that natural log to another series. A lot of times with something like this, you would say that because the natural log grows so slowly, it's not really affecting what's happening to this fraction. So in a lot of cases, you would maybe say that this is approximately equal to 1 over n. Now, if this doesn't work, you could try something else. But you could note that the natural log of n is going to be between 1 and n. So you can start here if you're not sure. And if you want to, and we're going to do this in another example also, you can go all the way up to here. We could have said, well, this looks like maybe n over n, but if it's n over n, then you are just left with 1, and that series would diverge, but it would be very hard to use that with a comparison, limit comparison, or wouldn't really tell you much, I guess. But we would say that this is the divergent harmonic series. And we'll use this as the comparison series. Now, if this doesn't work, you're going to find out quickly because you're going to apply the limit. And if the limit ends up being 0, then you know nothing. Because if the limit is 0 and your comparison series diverges, you know nothing. And then, you're going to have to come up with some other assumption. The reason I like comparing this to 1 over n is just because they're doing something that's so similar in this case. You're dividing by n. This numerator is growing really slowly. 1 is obviously not growing at all, but you're seeing this very similar type of behavior. If you're comparing natural log of n to n, it's not as close of a comparison. If you remember, I showed you this with my calculator, just sort of showing you that picture of what happens with that natural log graph. It looks kind of like this, whereas your regular function y equals n would look like that. And that's y equals the natural log of n. And of course, here's y equals 1. So you're just trying to sort of approximate what's happening with the behavior here. Working it out that way. All right, but let's go ahead now and we'll pop our limit in here as n approaches infinity. I'm going to take my series 1 plus n natural log n and divide it by n squared plus 5. I'm going to divide that by 1 over n. And then instead of dividing by 1 over n, I'm just going to multiply by n. So when I do that, I'm going to multiply by each term. I guess I'll show it in 2 steps. I was going to skip a step, but I'm going to show it in 2 steps. Don't want that n to get lost. So this is going to be n plus n squared natural log n divided by n squared plus 5. You might find it helpful to divide by, and you can divide by all sorts of things in this case. You might want to divide by the highest power in the denominator again, just because then you would be eliminating any sort of infinity over infinity situation. Technically, you could use L'Hopital's rule. I probably wouldn't, because I don't really want to take the derivative of n squared times natural log n. I know you guys might find it shocking that I don't want to take the derivative, but I don't feel like taking that derivative right now. I feel kind of chilled out. I don't want to get into that. So I'm going to divide each term by n squared. So n divided by n squared is going to give me 1 over n. In the next term, I'll have the natural log of n. And in the denominator, I'll just have 1 plus 5 over n squared. So when you're trying to take the limit as n approaches infinity, this is sort of your goal here, is to get your terms written sometimes as ratios where you have a constant in the numerator and variables in the denominator. And then what you're going to see here is that you're going to end up with 0 plus infinity divided by 1 plus 0, which is infinity. Now, this might seem terrible, but this is actually not a bad situation for us. If we end up with a limit of infinity, it's only a bad situation if the comparison series converges. But if I can go back to my theorem, however many examples ago, find it here somewhere. If the limit as n approaches infinity of a sub n over b sub n equals infinity, and if b sub k diverges, then a sub k also diverges. And our comparison series does diverge. So it's okay that we end up getting a limit of infinity in this case. We can say that because our comparison series, we'll call it b sub k, which we said was the series of 1 over n, diverges. Then we can say that both series diverge. And like I said, if it was the case that your comparison series converged and then you got infinity, well, you can't make a conclusion at that point. We don't have a theorem that covers that. You would either have to try another comparison series or just try a different test altogether. Usually you would just try to find another comparison series that would get you a different limit, which is what we're going to do next. Before I do that, does anyone have a question on example 9? I got one more in this section for you. I always feel like these natural log ones are trickier. There's a little bit more guesswork involved. With the other ones, it just seems like you just get from point A to point B a little bit more clearly. All right, last one for limit comparison series, limit comparison test, I should say. This is the series from 1 to infinity of, again, we'll use a natural log because it's good for us, of n divided by n to the 3/2. This is a tricky one. Okay, so last time in example 9, not last time, but in the last example, remember that when we had natural log n over n, we said that it was approximately equal to 1 over n because natural log n grew so slowly, we just kind of approximated it to 1. We're going to do the same thing here. We're going to say, all right, let's say that this behaves similarly to 1, not quite the same, but similarly. And n to the 3/2 stays in the denominator. And we'll use this as our comparison series. And this series converges because it's a p series where p is greater than 1
I found this on the web.
Oh my gosh, it's doing it again. You know what I think is happening? I keep saying series, and I think she's hearing me and she thinks I'm talking to her. Like Siri. I never talked to her, so I'm not really sure why she would think that. Now I'm interested in what she found on the web. All right. That's got to be what it is. Okay. Anyway, back to this. Let's go ahead and set up our limit. This is the natural log of n divided by n to the 3/2. Now, if you feel comfortable, like I said, go ahead and write that as a product instead of a quotient. I'm just, I've been doing it all along. I might as well stick with it for the last example. Okay, so this one clearly, when you multiply by n to the 3/2, ends up just being the natural log of n, which is infinity. Now, we got this result in the last example. However, in the last example, our comparison series diverged. In this example, our comparison series converges. So the fact that you got infinity, what does that mean? It does not mean that your series therefore must diverge because it's the anti-converge. That's not what it means at all. It just means you can't make a conclusion with this particular comparison series. Maybe your series converges, maybe it diverges, but you don't know. I mean, personally, I would look at this and think it probably converges just because of the denominator getting larger a little bit faster than the natural log of n. So this seems like it was a good idea, but it didn't work. So you can try something else. Remember, I stated up here that your natural log is going to be between 1 and n. So if you'd like, you could try the upper value here of n. We could approximate the natural log to n. It's not as close of an approximation, but we can still do that. So we can say that the natural log of n divided by n to the 3/2 is approximately equal to n divided by n to the 3/2. And sometimes with these natural logs, you're just going to be doing some guesswork. Now, if that's the case, n divided by n to the 3/2 is 1 over n to the 1/2. This series diverges. Interesting. So if we get this to work out and give us a limit that's either positive and finite or infinity, then we can say that both series diverge. So let's go ahead and apply the limit here. ln n over n to the 3/2. All right, instead of dividing by my comparison series, I'm just going to multiply by the reciprocal. I hope we're comfortable with that after this many examples. But now I'm changing it up on you. Makes me feel bad. Okay, when you cancel out here, remember that n to the 3/2 is just n times n to the 1/2. So if you cancel out n to the 1/2, that just leaves you with n in the denominator. Or you can, do the subtraction. 1/2 minus 3/2 is -2/2, which is -1, which leaves you with n to the 1st in the denominator. Now, you could use L'Hopital's rule here if you'd like, or you could just use the fact that n is growing more rapidly than the natural log of n. If you feel more comfortable using L'Hopital's rule, that's fine. You can do that. The derivative of the natural log of n is 1 over n, and the derivative of n is 1. And then as n approaches infinity, this quantity would approach 0. So this was not the situation that we were hoping for, because a limit of 0 is okay if our comparison series converges. Actually, it's great if our comparison series converges, but it doesn't. Our comparison series in this case diverges. I feel like I should sort of cordon this off here so you can see my attempts separately. So this was like attempt 1. And this would be attempt 2. Okay, so this is not going to work for us. The limit needs to be either infinity or positive infinite in order for us to get a conclusion of diverges. So we're going to need a different comparison series. Attempt 3. 3 times a charm. We're going to have to choose something that's somewhere in between 1 and n. A function that grows more rapidly than 1, which actually isn't growing at all, but a function that grows less rapidly than n. Did we already choose? Well, I mean, you have a lot of options here. Let us go with maybe, we'll write our series over here, ln n divided by n to the 3 halves. If we're keeping the denominator the same, maybe instead of going all the way up to n, maybe just use a fraction of that value. So maybe instead of n to the 1st power, you could do something smaller, like n to the 1/4 power. And you could play around with this if you wanted. You could try even n to the half. I didn't even think to try n to the half, although it seems like an obvious thing to do. But the goal is to pick something small. And sorry, I knew that was going to crash. There's just too much stuff over here. I mean, think about the way these functions behave. Sorry, I'm going to try to, I swear I'm going to end up downloading that emulator again. It's just such a hassle to switch back and forth. Natural log n, I'm going to graph that here. New natural log n x, we'll use x. And then you can use x to the 1/4 and kind of just compare and see what they're doing. And if you want, you could also look at x to the 1/2, which would be the square root of x. Again, just kind of looking at the behavior of these functions. Oh, I did not switch my window, and I got to wait for all 3 of these. There's the natural log. There's the 1/4 power. Oh, that looks pretty good. There's the 1/2 power. Actually, maybe my window is not so bad. If I set my y-min to be 0, I might get a little bit of a better picture. So that's natural log. Here's x to the 1/4, and here's x to the 1/2. I mean, either one's a good approximation. I'm sticking with the 1/4. If you want to try the 1/2 on your own, that's fine. You might even think that x to the 1/3 is a good compromise, or n to the 1/3. Try it. But we're just trying to look for a function so that we can simplify this down to a comparison series that we know something about that's approximately equal to these values. So the function natural log of n behaves very similarly to the function n to the 1/4 power, or the 4th root of n, if you want to think about it that way. That's the goal here. Keeping the denominators the same, then, we're switching these so that they're both the same type of function. As long as we have them as both the same type of function, then we can simplify this down to something we know a little bit more about. So if I take this and rewrite it, I know that this is n to the 1/4 minus 3 halves. It's equal to, it's not approximate in this case. 1/4 minus 3 halves is 1/4 minus 6/4, which is -5/4. So we're going to compare this to 1 over n to the 5/4 power. And this series converges because of the p series, where p equals 5/4. And I mean, this is like just converging. So if you were to try n to the 1/3, well, let's see, you would have 1/3 minus 3/2. You would also get another convergent p series. You would just get 7/6. So we talked about 1/3. If you did a half, though, you'd have 1/2 minus 3/2. You'd just have 1 over n, which diverges. So pick your poison there. Maybe I should write, could also do ln n is approximately equal to n to the 1/3 power. Okay, but we're going to stick with this. This one converges. Now, if I end up getting a limit that's 0 in this case, fine. My comparison series converges. So a limit of 0 means that my series would also converge. If I end up getting a limit of infinity, it tells me nothing. That would be like our attempt 1. If I get a limit that's positive and finite, awesome. Both series converge. So let's find the limit. This is the limit as n approaches infinity.
I didn't get that. Could you try again?
I don't even know. There has to be a way to turn that off.
I don't have an answer for that. Is there something else?
Oh my gosh, you guys. Okay. Where's my series again? ln n over n to the 3/2. My comparison series is 1 over n to the 5/4. So instead of dividing, I'm going to multiply by n to the 5/4. And then we get 5/4 minus 3/2. That leaves me with negative 1/4. So I'll have ln n divided by n to the 1/4 power. Okay. Wonderful. And then you can use L'Hopital's rule here if you would like. Again, you could consider growth rates of functions. I'm going to use L'Hopital's rule because that's what we've already done. So get 1 over n, and then we'll have 1/4 n to the negative 3/4. So this 4 is going to move into the numerator. And then the n is going to be in the denominator. The n to the 3/4 will be in the numerator. If you need to do a little bit of algebra to sort of swing everything around, that's fine. And then you can cancel again. This is just going to be 4 over n to the 1/4 power, which is going to be 0. That's okay because my comparison series converged. So hence both series converge. Just be careful. Sometimes we try to force these limits just so that we can get the desired result. So if you don't get your limit to work out, you're gonna have to try another series. There's no way around it. You can't just fudge your way through the limit and be like, it looks good to me. Because as you've seen, if you try to do that, you might get a completely different result than what you were expecting. And this is a hard one just because by eyeballing it, it's kind of hard to see what this series is going to do. Okay, so that's the last of limit comparison. I'm going to start talking about alternating series. Does anyone have a question on this one? I know I always spend the most time on the things I enjoy the most. It makes sense. This is why so many elementary school students don't know math, because their teachers don't like it and they don't want to talk about it. So they don't spend a lot of time on it, unfortunately. I know I'm grouping elementary school teachers into a bucket right now. I shouldn't do that. Some of them, I'm sure, have wonderful math skills. I actually really like my son's first grade teacher. She's awesome. And I'm sure her math skills are awesome. All right, alternating series. I'm going to give you a definition for alternating series. This is section 8.5. This is also going to talk about absolute convergence. It's just going to be part of a definition that we're going to go over, not like a big, huge deal. For the most part, I think you'll find the alternating series has to be super straightforward, easy to use. It will a lot of times require you to use other tests in conjunction with it. So that's the thing. Here's a definition for an alternating series. You saw alternating terms when we were talking about sequences in 8.1, but you have not really seen this alternating behavior with a series yet. An alternating series is either of the form k equals 1 to infinity of negative 1 to the k plus 1 a sub k. Now, if you had that situation, then your first term would be positive in this case. So you would have a sub 1 minus a sub 2 plus a sub 3 minus a sub 4, so on and so forth. Or you could be of the form negative 1 to the k instead of k plus 1. Multiplied by a sub k. So keep in mind, the only difference here is we normally just have a sub k without an alternating piece. So normally you have this series. All this is doing here by putting this alternating factor in here is it's just switching the signs of the consecutive terms. So this one is going to have a negative first term, because if we talk about k being 1, well, negative 1 to the first power is negative 1. And then, of course, if k is 2, negative 1 squared is positive 1. And you would get the same type of thing occurring just with opposite signs as we did with the first definition. Now, a sub k is positive for all integers where k is greater than or equal to 1. that's what an alternating series is. So these series are going to look very much like the series you've seen before. The only difference is they're going to have this added factor on them, -1 to the k or -1 to the k plus 1. And that's just sort of switching off their terms to the plus and minus. But you can see how these series would actually maybe can converge a little bit more easily, because instead of just adding a bunch of terms together and just sending them off to infinity, you're sort of keeping them in check by subtracting terms off of them. So you would be maybe more likely to see convergence here for an alternating series. Okay, I'm going to give you a test now for the alternating series, because there is a specific test to talk about this. You'll find that it's generally very easy to apply. Theorem, alternating series test. If the numbers a sub k, where a sub k is greater than 0, of an alternating series satisfy the two conditions, and I'm going to give you those conditions, two to check. The first one is the easiest thing to check. The limit as n approaches infinity of a sub n equals 0. The second one is that a sub k are non-increasing. Then the alternating series converges. Usually when I give this second condition, I would just say a sub k plus 1 is less than or equal to a sub k. Usually this is the way that I check this, and I say that this is true for some index k. So maybe it's not happening throughout its entirety, but at least at some point, this is true all the time. That's all that matters. But you're going to see that for most examples, this is going to be true for all indices k that are positive. So then the alternating series converge. I like to give all the theories in this section at one time instead of doing some examples like halfway and then adding on more examples that do the whole thing. So I'm going to give you the definition now for absolute convergence. A series from 1 to infinity a sub k is absolutely convergent if the series from k equals 1 to infinity of the absolute value of a sub k is convergent. So the absolute value of a sub k means that you're just taking the absolute value of each term in the series instead of changing the sign. So this would be just more like the regular old series that we've seen so far. So the absolute value of a sub 1 plus the absolute value of a sub 2, so on and so forth. So when you're thinking about absolutely convergent, you shouldn't be thinking about this as like, oh, totally convergent. When you're thinking absolutely, you're thinking about absolute values. So you're thinking about this series without the alternating pieces on it. And then there's one more theorem that I'm going to give you here before I give you some examples. And that would be the absolute convergence test. If a series, A sub k, is absolutely convergent, then it is convergent. So the absolute convergence is stronger than the alternating convergence. So if your series is absolutely convergent, then it's convergent. The other thing you're going to look at here is this definition I'm going to give you for conditional convergence, and that sort of goes along with that theorem. A series that is convergent without being absolutely convergent is called conditionally convergent. Okay, and I'm going to give you a bunch of examples after this. So like I said, I kind of like to lay all the groundwork before I start the examples. I like to present these definitions to you, and then I'm going to show you a bunch of examples where we use them. I don't have a ton of time to show more than maybe like 1 or 2 examples today, but I'll finish this up in the asynchronous lecture, which I'm actually going to record tonight.
I have a quick question.
Go ahead. Yes.
You said that absolute convergence is stronger than what? Because I didn't catch the last part.
Then alternating convergence.
Okay.
So
Thank you.
no, I'm really glad you asked. So remember we were saying on this first page when we were looking at the alternating series, the fact that you have the pluses and the minuses means that the terms in this series can't grow as quickly. You're adding terms and then you're subtracting off terms. So the alternating series is more likely to converge than the absolute value of the series. So you might have a series where if you were just looking at a sub k, maybe it diverged, but as soon as you turn it into an alternating series, it'll converge. Just because you have this situation where you're subtracting terms off, and that might be enough to limit its growth. that's really the difference here between absolute and conditional convergence. So it's possible that your series can converge, but if you were to take off the alternating factor, it would diverge. And in that case, you would say that the convergence is conditional. And it's conditional on the basis that the series alternates. So if the series didn't alternate, it wouldn't converge. That's conditional
okay.
convergence. Yeah, I'm glad you asked. I know some of these things, like I could write out paragraph explanations that I feel are better, but then nobody wants a paragraph. So I think though, getting used to seeing some of these and kind of watching how they work will really help to solidify this idea. So I'm going to show you, see what I have here. Oh, I was going to try to show you one really quickly where you had that situation occurring, but oh yeah, okay. So let's look at this one, for instance. Example 1. I'm going to do a compare and contrast. I have 5 minutes. I can probably do these two. If not, oh well, we'll finish it in the async lecture, which I'm recording tonight. Okay, so the first example will be -1 to the n plus 1 divided by n squared. Now, if you were to see the absolute value of this series, the absolute value of the series, well, okay, think about this. A sub k, in our case, is going to alternate. So you're going to have -1 to the n plus 1 times, well, it's a sub n in this case. If you were to put absolute value bars on that, you would be eliminating this plus and minus between the terms, and you would just be adding all the terms together. But what we're going to do is discuss the convergence of the alternating series. Now, one of the things we're going to check for that is the limit. We're going to take the limit as n approaches infinity of a sub k, or in our case, a sub n. A sub n is the piece that doesn't include the alternating portion. So a sub n is just going to be 1 over n squared. The alternating piece is -1 to the n plus 1. So you're going to take the limit of a sub n, or a sub k, however it's written for you. If you get 0, great. That's one condition that needs to be met in order for the alternating series to converge. Just this alternating series has something to do with this, but they don't necessarily do the same thing. The next thing you're going to do is show that the n plus 1th term is less than or equal to the nth term. So we're going to show that the n plus 1th term is less than or equal to the nth term. So if you want, you could even say, okay, number 1, number 2, I have to meet these two conditions. The n plus 1th term for a sub n is going to be 1 over n plus 1 squared. And you're trying to show that that's less than or equal to a sub n. This must be true. It has to be true. In this case, you're adding a value to the denominator and then squaring it. So if this is n plus 0 squared, this is n plus 1 squared, this denominator is larger. Therefore, the ratio is smaller. These are constants in the numerator. So as long as you write this down, if it's self-evident, awesome, show me. I'm not going to put one of these on your test where you're going to have to use the first derivative test. Most of these are going to be pretty clear to see. You might see one occasionally on the homework where you'll have to use the first derivative test. I believe I have one scheduled for you in the notes. Yes, I do. And then we'll discuss that on the async lecture. Just you've done it before, but I want you to see it again. As long as you've shown that these two conditions are met, then you would say hence the alternating series is convergent. That's it. It does not matter what else is happening in the series. Whatever this is, all you need to know is that its limit as n approaches infinity is 0, and that the n plus 1th term is less than or equal to the nth term. Those are the two things you need for the alternating series to be convergent. Now, the conditional and absolute convergence comes into play when you look at the actual series 1 over n squared. So if we're talking about absolute versus conditional, this is where we need to look at 1 over n squared. And I gave you a definition for that. Oh, if a series is absolutely convergent, then it's convergent. If it's convergent without being absolutely convergent, it's conditional. So what I'm going to do is look at this series. A sub n is 1 over n squared. This is a convergent p-series. So since I know this is a convergent p-series, I know that this series is going to converge regardless of whether it alternates. So I would say that our series is absolutely convergent. Because it's going to converge regardless of whether those terms alternate. Some of your homework questions are just going to ask you, does the alternating series converge or diverge? Others are going to ask you some additional pieces to this, like is the convergence absolute or conditional? Conditional convergence would be if your a sub n diverged. So if this was something like, I don't know, 5 halves to the n, you'd be looking at a divergent geometric series, and that would diverge, but you would probably check these and make sure you would still get the alternating series to converge. And I'll show you another example where that happens also when I go through the asynchronous lecture. But this is enough to sort of get your feet wet. I'm going to put up the async lecture, and any of the homework from 8.5 that I put in there will be due a week from Monday. I won't add it in with tonight's stuff because I didn't really even hardly start it. So the homework that will be due next Wednesday will be the limit comparison test from 8.4. Okay, oh, I also wanted to mention, oh, I owe you like 2 minutes now. Thanksgiving break, we do not have class that day. So I totally meant to email you and tell you, and then I got lost in the crazy weekend that's going on over here. That's over, but it still feels like it's going on because like everybody's a Scorpio around here and they're just birthdays out the wazoo. So no class the 24th, which is the day before Thanksgiving. I verified that with the school office. So yay, we don't have any class. No class Wednesday, 11/24. So you're off the hook. I will outline what my plan is for the rest of this schedule when I go through the asynchronous lecture with you. I meant to put it on here, but I'll go through it. Basically, I'm planning on doing asynchronously, finishing 8.5, at least starting 8.6, if not finishing it. We'll see. It's a little bit of a shorter section. 8.5 really isn't that long either. And then I want to talk about power series next Wednesday. And then you would have your test then a week from next Wednesday. So if next Wednesday is the 10th, you'll have your test the 17th, which is the way it was scheduled on your syllabus as the 17th. I think though for your asynchronous lecture, that's technically the 15th. I'm just going to start chapter 9 because I don't want to do new material that you're going to be tested on asynchronously. I just don't want to do it. And we need to get started on chapter 9 because we're not going to have class on this day and I don't want to cram it all in at the end. So I'm going to start chapter 9 on the 15th, 9/1, 9/2 on 11/15 async, which will of course be delivered to you prior to 11/15. So you'll have it before your test, but I don't know what else to tell you. It's not that hard. 9/1, 9/2. pretty straightforward. Test 3 on 11/17. And then you'll, of course, have asynchronous lecture again the 22nd. So you would have a lot to do there potentially if you didn't do that before your test. But I guess I don't need to go through this again because I'm showing it to you right now. I'll probably just do a reminder. But that's my plan. Anyway, now I owe you like 4 minutes. If you want to stick around for the office hour, be my guest. Otherwise, email me if you have questions. I'll put up some homework from 8-4 to finish that out. And I'll see you next Wednesday for some power series. Yes. Good night.